So your talk just now for our center revealed some things you're working on that aren't published yet, and therefore this particular film won't be shown until they are published, about using neutrality to make predictions about loci on the human genome without knowing anything about the human genome, only from other species. Is that the basic core idea?
Yes, that is the basic core idea. And so the idea that we had was that we have history of human species from chimpanzee, gorilla, orangutan, gibbon, all of these species.
And we have the sequence for all those other species.
And we have their sequence, genome sequence in a very high quality now. And humans share their ancestry with them. Really, human and chimpanzee diverged 5 to 7 billion years ago. So if you think about our ancestry with zebrafish and frogs and chicken and all of these species that are sometimes we can't even think about as having ancestry with, we are actually related to all of them and share history over 500 million years.
So you can make a prediction for on chromosome 5 at this particular location. How likely is it that changes there were neutral? Is that how you would say it?
That's right. So if you look at this tapestry of life from chimpanzee all the way to fish, and you can go to a position in the chromosome and say, what do they have?
What do they have?
What do they have tells you that what has been allowed by nature to persist.
What should we have if you're making a good guess?
Yeah, so in that case, that gives you an idea of if fish and dogs and chimpanzee has a state or DNA state, then you can pretty safely believe that humans might also have it.
And if they don't,
yeah, then you know that
something is happening.
That nature has already made mutations in all species because of the time elapsed is so long and mutations happen all the time. They must have been eliminated by nature in the past through the process of negative selection. And essentially in this case, if you observe a DNA state in humans that has never been found elsewhere, it is an unlikely event. And
so some is eliminating things, but the other is changing two different positions. And if you find one of those, so people have worked very hard to try to figure out protein variations that are adaptive. And they haven't found very many, right? How many have they found?
Well, they have found anywhere from 25 to 30, the ones that are considered to be bona fide. Yeah.
But your new method expands that dramatically.
That's right. So what we did is we took the data from other species and we then used a mathematical framework to predict what the human genome sequence should look like. And then what we found is for essentially all 99% of the positions is exactly what you expect. So humans have the same.
No surprise there,
No surprise.
Neutrality, fine.
Yeah, it's all great because it's as expected.
Right.
But the fun part was when we found that there were many thousand positions.
So 5% is quite a few still.
5% is quite a few. So in our case, we found around 18,000, which is around 4% of 500,000 positions. So we found that as many as approximately 20,000 positions are not behaving as expected by evolution.
By neutral evolution.
By neutral evolution.
So this suggests what?
So this suggests that these positions are able to harbor a DNA or protein change that is otherwise function impacting.
So people have looked previously with several different mathematical models to try to figure out where evolution is happening in the genome based on how similar DNA is adjacent. This is a new method.
It's a new method because what we did is we did not use the data from humans for that position when we make predictions about that position. And then we say, if this is the expectation or our null starting point, then is it consistent with what we observe in humans?
Right.
And then we go to that position and we look at humans and what number of people have that particular mutation.
Right.
And you find that a lot of people have this change that is completely unexpected.
So if it's common and it's different from what you expect, something's going on and you put on your detective hat.
Yeah, that's right. And that's what we call CAPS, to go with hats.
What does CAPS mean?
Candidate Adaptive Polymorphism.
I predict people will hear a lot more about that in the next decade.
Well, we hope it is very useful. But with the CAPS, the interesting thing is they immediately provide you by doing only computation. Remember, we are not doing anything in the laboratory. We are using available data on the internet that many scientists have accumulated in many laboratories. And we are able to use that data, multitude of that data together by synthesizing and generating predictions. And CAPS is a prediction because it is potentially adaptive polymorphism.
So it's giant use of giant new big genomic data, plus mathematics that's actually quite sophisticated when you do it.
Yeah.
But the core idea remains quite simple,
Very
isn't
simple,
it?
yeah.
If you find something that's not what you would expect from neutrality based on other species, and it's common, then something is happening.
Something is
that's
happening,
interesting.
yeah.
I think this has huge opportunities.
Yeah.
Thank you. Great.